Okay, so organic chemistry has been technically removed from the AP, as well as nuclear. However, I think it's crucial for you to know the simplest basic components of this. Because if you go to college, it's kind of expected when you go into a general chem class, even in bio, there's some expectation that you know some of this stuff. So I'm minimally covering it, and you're not even being tested on it. We're just having a group quiz on it. Okay, so utilize this as just making your bank of information a little bit bigger. If you take organic chemistry next year, I do expect you to know this. So if you know you're taking it, know that this is coming, so you might as well start learning it now. So what we're going to start with is just, all we're doing now is nomenclature. And today we're going to just look at nomenclature of hydrocarbons, which is just hydrogen and carbon combinations. Hydrocarbons that we're specifically looking at are alkanes, alkenes, and alkynes. Alkanes are specifically hydrocarbons that has carbons that are singly bonded to each other. And then they're fully saturated, which means no double or triple bonds, fully saturated with hydrogens. The general formula for a hydrocarbon is going to be this: CnH2n plus 2. So you can look at a formula. If it's C5H12, you can go, oh, that has to be a hydrocarbon. I mean, shoot, has to be an alkane. That has to be an alkane, so that'll give you some clues as to how you can draw it. All right? The prefixes for alkanes and alkenes and alkynes are the exact same. What's different is the ending. So you need to know all these prefixes, and then if it's an alkane, it has an ane ending, alkene has an ene ending, and alkyne has a yne, an ine ending. So if it's 1 carbon, meth, 2F, 3 prop, 4 but, 5 pent, 6 hex, 7 is hept, not sept. Do I need to come over there and turn things off and take away iPads? Turn forward, Miles. Feet in front of you, and stop talking to him. 8 oct, 9 known, and 10 is dec. Okay? All right. The way you name them is going to be based on arrangement, which we'll talk about. The other things you need to know other than alkanes are cycloalkanes. Cycloalkanes are going to have 2 less hydrogens on them. Can anyone tell me why? Exactly. When they make that ring, those terminal hydrogens have to come off in order for the carbons to connect. So they're going to have the actual same general formula as an alkene does. An alkene is something that just has a double bond in it. For the most part, we're only looking at things with 1 double bond or 1 triple bond. We're not looking at multiple double and triple bonds. Okay? There's no way to look at the formula C5H10 and know which one it is. You just have to be given more information. These are actually called isomers of each other if you were to draw them, and we'll also talk about that today. Alkenes have that ene ending in front of one of the prefixes from the previous page. And then alkynes has a triple bond somewhere, and it's going to have even 2 less hydrogens than the other. Because we have a triple bond, we lose an additional 2 hydrogens, and it has a yne suffix. So I'll go through, I'm going to read the list of rules, but you'll really see the rules in action when we just start naming. So we're going to combine a prefix with a suffix. The first thing you do when you see a structure is find the longest continuous chain. So you're going to put your pen on the paper, and you're going to just drag it through the carbons until you find the longest chain. That is what I call the parent chain. And off of the parent chain, you might have some things like groups. Those groups are called substituent groups. The way you name those, same prefixes, but instead of an ane or an ene ending, you end it with a YL. We call them alkyl groups, so we end it with a YL. So that would be a 1-carbon group. Ending with a YL is a methyl. If it were a 2-carbon group ending with a YL, it would be an ethyl, and so on. Okay? Then you have to tell me where the alkyl group is by positioning, telling me a number. All right? You always number from the side that puts the alkyl group on the lowest number. So let me make this chain longer. If I were to number this, I would number from this carbon because that would put my methyl on 3. If I were to go this way, 1, 2, 3, 4, 5, that would put my methyl on 5, and that would be the wrong way. All right? What we're doing now, by the way, is called IUPAC nomenclature, International Union of Pure and Applied Chemistry. I see it as a bunch of old men in white coats sitting around a table making stuff up. It's pretty much what it is. This is all just a bunch of rules made to a system that everybody uses. If you have multiple substituent groups that are identical, you use di, tri, tetra in addition to numbers. So let's say I had that. This is 1, 2, 3, 4. This would be a 3, 4 dimethyl group. We wouldn't say 3-methyl, 4-methyl. When the groups are identical, we combine them and we say 3, 4 dimethyl, whatever. If they're on the same carbon, we'd say 3, 3 dimethyl. So the number of numbers needs to match. Like if you have the prefix di, you need to have 2 physical numbers. If you have tri, you need to have 3 numbers, even if it's a repeated number. And again, we'll practice this. If you have different kinds of substituents and you don't know how to name them, what goes first, you name it by alphabet, not by position. So if I have an ethyl on 4 and a methyl on 3, I would name it 4-ethyl, 3-methyl based on the alphabet, not based on the fact that the methyl is lower in number. Okay? It's alphabetical that we look at. And then if you do have a double or triple bond, say you have a double bond, the double bond will come into, has to be on the lowest carbon. So we have to number from that end. That takes precedence over any group we put on there. The double bond takes precedence because it changes the base name. So that has to be on the lower carbon. It also has to be a part of the longest chain. And again, we'll practice it. So let's look at some compounds. Now, let's talk about this format. You guys are no longer allowed to do this. I'm not going to sit there and check all your H's. Not doing it. I don't want to see this. I want to see line structures. Line structures is what you see above, and this is actually, above is a program that put terminal carbons on there, and I didn't know how to turn it off until a year later, but this doesn't have to be there. It's the same thing without it. But ultimately, what a line structure is, an intersection or an end of a line represents a carbon. So 1, 2, 3, 4, 5, 6, the line structure of that, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That is the same thing as that. We assume full saturation of hydrogens wherever we have a carbon. So with this carbon, how many hydrogens do we have? 3. At this carbon, we have 2, 2, 2, 2, 3. If I'm in an intersection like that, that's a carbon, a methyl group hanging off of this guy. So how many hydrogens does he have now? 1. That's all assumed. Okay? If I had a double bond, how many hydrogens are here? 2. And how many here? 1. Okay? So that makes life a lot easier for everybody, you and me included. So don't freak out if you don't have the terminal C's like these. They're not necessary. Okay? Just know they're not necessary. So I don't want to start out with this one. This one's a little convoluted. So let's just start out and find our longest chain. So of this guy, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. I think that's longest. Let's just check as we go down. 1, 2, 3, 4, 5, 6. So going across is the longest chain. All right, so it's a chain of 6 with no double bonds. What's its base name? Hexane. All right, this is a methyl group, and this is an ethyl group. What carbon is the methyl group on? Which way do we number? Exactly, that's 2, and this is 4. So if I number this way, we'd have it on 1, 2, 3, 4, and 5. 1, 2, 3, 4, 5. Oh, this is not hex. It's 7 of them, so it's hept. Okay, so now we name them alphabetically. What comes first? Ethyl. So we call this 4-ethyl 2-methylheptane. Do y'all see it? Okay, the next one. I'm just going to fly through this, so if y'all have questions, ask me. First period was ask me a question, every single one. I know you have questions, you're just choosing not to ask them, and that's your deal. You want to ask me a question, I'll stop. 1, 2, 3, 4, 5. Base name. Okay, good. 1, 2, 3, 4, 5, 6. So that's a long chain, that's a substituent. Hexane, what kind of hexane? 1, 2, 3 or 1, 2, 3, 4. Which one is it? 3-methyl hexane. Technically, and I'm not going to freak out about it, but technically there should be a hyphen between numbers and letters. There should be commas between numbers. So if you have 3, 3, it's 3, 3. And then this, whatever is right in front of the base name usually attaches as part of the actual word. But again, I'm not going to lose sleep over that. Not this year. Next year, different story. So this one, we'll start here. This is obviously going to be longer this way. 1, 2, 3, 4. It doesn't matter. 5. All right, that's a chain of 5. That's a pentane. And then what do I put on that? I've got, there's a 2 and a 3. Not 2,3-methyl. Exactly. 2,3 dimethyl. If I have 2 numbers, I need a di. If I have 3 numbers, I need a tri. Now, I want to revisit this one. Your inclination might be to make this the longest chain, but you have, notice here you have one really weird-looking group hanging off of it, right? You need to check this way out because this is the same number of carbons. This is 1, 2, 3, 4, 5, 6. This is 1, 2, 3, 4, 5, 6. We number it this way. The reason we number it this way is the rule is you want to number the longest chain where you have the most substituent groups. When we numbered this way, we only had one big funky group. When we number it this way, we get 2 simpler groups. All right, so 1, 2, 3, 4, 5, 6. What is this? A hexane? We have a methylon 2 and an ethylon 3. What do I name it? Yes. 3-ethyl 2-methylhexane. 3-ethyl 2-methylhexane. Yes. Why do we always put the ethyl before the methyl? Alphabetization. Okay, let's keep going. This one's easy. Longest chain's pretty easy to see. 1, 2, 3, 4, 5, 6, 7. Heptane. 1, 2, 3, 4. Either direction is 4. 4-methylheptane. Good. Let's go to this other straight chain. 1, 2, 3, 4, 5, 6. This is hexane. Now, one thing I want to point out, there's going to be a point where I want you to come up with isomers, meaning different arrangements of these carbons. Anytime you have single bonds, you have full rotation around the carbons. So this chain could chink in different places and still be a hexane. So if I had this, that is the same as that. Don't think that's a rearrangement of that. It's the same thing. There just happens to be a bend somewhere else based on just single rotation. Those single bonds are free rotating bonds. All right, this one. 1, 2, 3, 4. 4 is going to be it because 4 would be finished out by either of those substituents. So, just all together, what's the name? 2,2-dimethylbutane. That is because it's an intersection. Anytime there's an intersection, it's a carbon. Another common error here, students want to call these two in combination an ethyl group. No. An ethyl group, the carbons have to be attached to each other in that same part. Here they're not. They're each separately attached to that base chain carbon. Do y'all see the difference between an ethyl and a dimethyl? This is the exact same compound. Again, My point is, based on the free rotation, you need to name it to show it's the same compound and not think it's something different because it looks different. Okay? This is the exact same compound. Let's keep going. Don't let this one freak you out. That is a carbon. The simplest. What? Methane. This is CH4. That's all it is. Methane. Okay, the next one to the right, we have triple bond connecting two C's. What? Two. Not seen. Sine. S-sine. E-T-H-Y-N-E. Now, normally you need to put a number indicating what carbon that double or triple bond comes after, but because there's only two carbons, it has to be after carbon 1 from either direction. So we don't have to put a 1 there. It's actually bad form to put a 1 there. All right, let's go over to the next one. We're going to number this 1, 2, 3, 4. The double bond location takes precedence. Notice the double bond, either way we go would be after a carbon 2. If we went that way, it's carbon 2. If we went the other way, it's carbon 2. Which carbon do you think, just gut, do we make carbon 2? Correct, the one on the left. Why? It then has a substituent group. But the substituent group is not making that determination first. First, it's the location of the double or triple bond. So this is going to be a 2-butene first and foremost. Okay? And then we have a 2-methyl on it. You have to say 2-butene because I could have a, is it bute? Yeah, because I could have a 1-butene. I could have the double bond here and the substituent still here. If that were the case, if the double bond were here, it would be the 1-butene, and this would be then on carbon 3. So it would be 3-methyl-1-butene. The double bond takes precedence. Anything that changes the name takes precedence over the substituent groups, like alcohols or OLs on the end. Those take precedence over methyls and ethyls. Ketones, aldehydes, all change the base name, so they take precedence over substituent groups, okay? All right, what's this one called? 1, 2, 3. Propene. Do I need a number? No, because if I have it here, it's after carbon 1. If I have it here, it's after carbon 1. There's only one way to have propene, and it's 1-propene, so you don't need to list it. Okay, let's look at this one. Just a little bit of a twist. I'm not going to even do the other one. No, I will do the other one. No, I won't. Yes, I will. Okay, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Were you getting 2, 2? 2, 3, 4. 1, 2. That would be 3, 3, 5. You go to the side, you hit a substituent group first, okay? So this would be 2, 3, 4, trimethyl. How many were in the chain? I don't remember. This one, the longest chain is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 1, 2, 3. So this would be 3, 5, 5. This would be 3, 3, 5. Which one do you think? 3, 3, 5. Trimethyl heptane. Okie dokie, Smokey. From now on, I'm just doing the double bonded, triple bonded ones because I think you've got this other stuff under control. 1, 2, 3, 4. Remember, it's the carbon, the double bond is after. So what do we want to make carbon 2? The one with the methyl. So it's 2-methyl, 2-what-ene? Butene. 1, 2, 3, 4. What's the name of that? Nope, not butene. I would count that wrong. 1-butene. I can have 2-butene. Can I have 3-butene? Nope, because I could number it the other way and get it lower. What's this one? Cyclopentene. Now, it is cyclopentene. You don't need a 1 on this because it's a circle. All right? So that is always going to be carbon 1. So if you have substituents, say you have this coming off, this has to be carbon. One of these two carbons has to be 1. And remember, it's where the double bond comes after. If I make this carbon 1, that means I have to be going that way because the double bond has to come after the carbon. Is that the best way to go, considering where your substituent is? No. So we think this is carbon 1, 2, 3. Numbering that way, it would be a 3-methyl cyclopropene. Yeah, pentene. It's an aromatic. The specific one that you're going to need to know is benzene. We'll talk about that tomorrow. He's saying the word that describes alternating double bonds. It's in a 6-carbon ring, and it looks like that, and it's called benzene. Sometimes they draw it like this. Okay? And that just means these double bonds are existing. And with something called resonance, they can all hop over to different carbons. The pi bonds can break and reform. And we'll talk about that a lot more next year. Let's name this one real quick. 1, 2, 3, 4. What is it? Oh, it's exactly the same as that one. I have the same 2 on the same page. This is the same as that. Okay. All right. What's our longest chain on this one? 1, 2, 3, 4, 5, 6, 7. One on the homework, I already messed up on the key, by the way. One of them, there was an ethyl group near the end that I didn't count up, and the longest chain I chose was wrong, so just be aware of that. All right, what is this? 2, 2, 2, 2 what? It's 6. All right, this one throws people off. There's a difference between this. Is it heptene? And it's tane. There's a difference between that and that. Do you see the difference? Do you see it? What does this mean? There are carbons there. So there's 2 carbons in this one. There's 4 in this one. So what's the name of that one? 2-butyne. Good. All right, an isomer. An isomer is a structure. Our isomers are 2 structures, or a structure compared to another structure with the same general formula, or same formula. Now, they're going to have different properties. There's different kinds of isomers. We're going to focus just on 3 kinds in this year. Next year, we're going to go isomer crazy. It's a big deal in organic. What an isomer is, again, all these things we're talking about have the same exact formula. So, for instance, the first type is structural isomers. Structural isomers is just a rearrangement of these 5 C's and 12 H's. You have to follow the rules. Everything has to have 4 bonds, except hydrogens have 1 bond, and you have to have the same number. So if you look at this, we know that C5H12 is straight up pentane. Because of this general formula, do you agree it always has to be an alkane? Yeah, we cannot have an alkene or an alkyne come from this, because that would change the number, that would change the formula. So if you look, here we had a long chain of 5. The way you figure out how many isomers is you'll take one off the long chain and then make it a substituent group and put it on a shorter chain. So we have a methylbutane, and then we took another one off and we had a dimethylpropane. So structural isomers have different names, but the same exact formula. This pentane, again, students will do this and go, oh, this is an isomer too. That's an isomer of that. No, it's not. 1, 2, 3, 4, 5. Well, that's not even the right one. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Same thing. Free rotation around single bonds allows for that. So these are the exact same compound. The way you keep yourself from making this mistake is after you draw something, name it and see if the name's different. Okay? The other type of isomer you need to know is something called a positional isomer. This is easy. This is the difference between like 2-propanol versus 3-propanol. The things that change the name, like alkenes, alkynes, the difference between 2-butene and 3-butene. The difference between 4-decene and 5-decene. Okay? That's a difference that we just call a positional isomer. That's really easy. And then the last one is a geometric isomer. And this has to do with the existence of a double or triple bond. You cannot have geometric isomers unless you have double or triple bonds. And what's happening here, because of this double bond, this pi bond, y'all remember pi bonds overlapping? Because of that pi bond, it locks it in position. It can't free rotate. So we have a position where we have these CH3s in the long chain on the same side of the double bond. This is going to be a different compound entirely. It has totally different chemical properties. It's going to have more strain. It's not going to be as stable as that other one. And that's because these guys from the long chain are on the same side. If the long chain falls on the same side of the double bond, we call it cis. Draw your long chain on this one. Do you see how the long chain is transfers across? We call that trans. So you always just write the word cis or trans on the other side. You can't tell me if something is cis or trans unless you have some direction. Like here they drew it in a way you would know. If I would have drawn butene, 1, 2, 3, 1, 2, 3, 4 like this, and put the bond like this, there's really no way for, well, I guess you could. It would look like that. So yeah, you could. I take back what I was going to say. So this would be up here, trans, and this would be cis. Okay. So let's go ahead and start practicing with a few isomers. Write the structures for the 3 isomers that have the formula C5H12. So I'm going to show you my method, and then I'll let you practice it. 1, 2, 3, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we know that's the basic pentane, right? Now I want to try to come up with another structural isomer. So I always just make it a chain then of 4, take one off, and then place it in as a methyl group in as many places as I can to get different structures. So where do you want to put it first, the methyl group? The second. Can I put it on one of these? No, because I'm just lengthening the chain back to pentane. I'm not doing anything. So this is 2-butane. Okay, thinking back, I have that methyl group. Could I have put it here? I could. What's the name of this and what's the name of that? They're the same name. So this is not a separate isomer, okay? So I think I'm done with my 4 chain. Now I'm going to make a chain of 3. Remember, now I have 2 methyl groups hanging off. I can place them as 2 methyls, or I can put them together and make an ethyl group. So let's place it as 2 methyls. Where would be the only place I could put 2 methyls? On carbon 2. And that's a 2,2-dipropane. All right? So that's all I can do. If I were to put one on the end, I'd be back at this. So the last thing I want to do now is decide, can I place those 2 as an ethyl group? It's the same as that guy, so he is not a different isomer, a structural isomer. So these are really my only 3 isomers for this guy. All right? Let's do another one a little bit more complex. Write the structures for the 5 isomers of C6H14. So start with your straight chain, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This is that's a hexane. So now I'm going to make a chain of 5, 1, 2, 3, 4. And this is just my method. You don't have to use my method, but I have my methyl group. Where can I put it? Carbon 2. All right. Can I put it anywhere else? Carbon 3. Nice. I can do that. Am I done? If I moved it over one more, I'd be back at carbon 2, so I'm done with the methyl and the 4 chain, or 5 chain. Now I'm going to make a 4 chain. 1, 2, 3, 4. Now how many methyl groups do I have? I've got 2 methyl groups. Where do you want to put them? Not 1, 2 and 3, okay? I can actually put them another combination. 2 and 2. Can I put them on 3 and 3? No, because it would just be 2 and 2. Now, I have those 2. The last thing just to check is, can I, 1, 2, 3, 4, can I put an ethyl group? Let's just do it. What did that do? 1, 2, 3, 4, 5. That brought me back to this. So I'm done. When you get to the point where that's happening, you're done. Because if you're making it any shorter beyond that, it's just going to get worse. So y'all good? Did we draw 5 of them? Yeah. Now, I'm nice to you in this class. In organic, I don't say how many there are. And they just have to keep drawing and drawing and drawing until they. And then at one point, one student apparently didn't get it one year and drew like 12 of those, all different shapes. Like, I was like, oh, yeah, you don't know what you're doing. Okay, we're almost done. Now we're going to kind of go backwards. Draw the structures for cis and trans isomer of chloroethene. All right, what does chloroethene start out looking like? Its base. I mean, just ethene, excuse me. Ethene. What is ethene? 2 carbons with a double bond. Okay, so there's the base of it. Don't let the halogen scare you. It's dichloro. What do you think that means? 2 chlorines. That's it. Okay? So we have a chlorine on 1 and 2. How do I make them cis and trans? 1 up. If I do them both up or both down, what is that? Cis. I would go ahead and just put your H's in here. You don't have to, but I would. And that would be a cis version. And then what would the trans look like? Correct. Okay. Don't draw this, but I had a good question last period. The question was, can you be trans like this? There's a bigger problem than that. Name that. No. Doesn't violate the octet rule. Name this compound. If that's 1, 2, what's this one? That's 1, 1. So it's not even a 1, 2. So as far as cis and trans goes, this does not have cis and trans properties. Because if I break this bond, rotate it, would it look any different? I'd still have 1 Cl above and 1 Cl below, no matter what I do. Okay? All right, so now we're going to draw. The drawing is so much easier than the naming, because you know that we have a propane, meth, S, prop, 2,2-dimethyl, 2 methyls on carbon 2. 3-hexyne is a chain of 1, 2, 3, 4, 5, 6. And after carbon 3, I have a what? No, triple bond. 3,4-diethylhexane. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, diethyl. One, 3, this is throwing a little wrench in. I'm giving you this to show you that you can figure out more than what you think based on knowing a little bit about these IUPAC rules. 2 double bonds. Good. So if we have pent 1, 2, 3, 4, 5, where would those 2 double bonds be? After carbon 1 and after carbon 3. So you can expect maybe sometimes things like this to show up on the AP, but you have enough knowledge, not in organic, but you have enough knowledge to figure things like that out. That's why I can't cover everything the AP is going to have on it. You have to use stuff you already know to figure as tools to figure out what you need. 3,3-dimethylcyclobutene. Cyclobutene. So agree that's cyclobutene. All right. Nah, what am I missing? Got to have a double bond. So I'm going to make that. I have to make that double bond carbon 1. If I put the carbon 1 here, that means I got to go that way. So that makes this 1, this 2, and this carbon 3. So then I just have 2 methyls coming off of that. You don't, not on the picture, no. I'm just doing it in teaching. No, I prefer if actually you didn't have numbers on them. All right, so that's it for today. I won't see you guys tomorrow. You'll be at Junior Career Day, but we will do this on Wednesday. Review process explained Thursday. Group quiz on this stuff Friday.